So, welcome back to this video series again about material phenomena in nuclear environments. So we want to continue the discussion of thermal stress. So we previously introduced you to the concept of pressurized thermal shock, or PTS. Yep, this is the diagram we have talked about before. Now where the reactor goes through PTS, and that is during an emergency core cooling shutdown kind of incident. So during any emergency where the control rods are inserted into the reactor core, there will be a certain amount of water that needs to be pumped into the core to keep it cool because of the decay heat that must be removed, otherwise there is a meltdown. But doing so very suddenly can cause a huge temperature differential and cause some thermal stresses, and this is what is called PTS, or pressurized thermal shock. So what role do neutrons in the RPV, what role do they play in determining the response to pressurized thermal shock? So what is the role of neutrons here? Well, firstly, we'll need to know something about ductile to brittle transition, and that's what this DBTT stands for: ductile to brittle transition temperature. If you're not sure what that is, there's a link in the description below. And the idea is that about this ductile to brittle transition, the idea is that if you take a piece of steel and let's say you pour liquid nitrogen on it, so you have some steel here, you pour liquid nitrogen on it, Ln2. So what the liquid nitrogen will do is not only it will start lowering the temperature, it will lower it so low until it's very fragile. And if you drop this piece of steel on the floor, it will start to shatter and break. You have probably seen some interesting videos like that before. So I'll just put one in the link because yeah, these kind of experiments are pretty fun. So if you soak a flower or capsicum or bell pepper or even a log, it becomes really easy to break. But at room temperature, this same piece of steel, or this same log that we are talking about, like a metallic log, it becomes much harder to crack. So somewhere between room temperature and minus 196 degrees C, which is the boiling point of nitrogen. So room temperature is around 27, 25, 20, thereabout. Somewhere in here is the ductile to brittle transition temperature. And this is a phenomena that happens mostly for BCC structures. It happens for BCC structures rather than FCC. So FCC don't have this effect. So that means gamma steel, gamma iron, or austenitic. So austenitic stainless steel, they are sort of more immune to this effect. That results in them being used for cryogenic applications. They are very good material for that. So anyway, back to our discussion about neutrons. We know that about neutrons, when there's neutron damage, one of the primary effects we are concerned about is embrittlement. So that means at the same temperature, for example room temperature, the same material becomes more brittle. So if one were to draw some graph of temperature versus toughness, or toughness versus temperature. Toughness versus temperature. And then you have something like 27 degrees C. So this toughness will drop because of radiation. So this is the unirradiated sample. And this is irradiated. So the toughness will decrease for a given temperature. So at the same temperature, the same material becomes more brittle. So it decreases the material toughness. So the other way of saying this is that the other effect, if you consider this, is that the ductile to brittle transition temperature increases. So how does it look like on the graph? Okay, so let's say we have a graph here of toughness versus temperature. Okay, so if this is the original curve, okay, so let's say somewhere here is a ductile to brittle transition temperature. So this is for BCC. Okay, so BCC will exhibit this behavior. Okay, so what happens when you irradiate it? So the toughness at every temperature will drop accordingly. So the toughness drops. So the toughness drops at every temperature. That's what embrittlement means. So this is irradiation. Okay, that's the irradiation thingy. But what happens at the same time? Okay, let's say this is the same temperature. So, yeah, this is the same temperature. And, oh, this is the same toughness, sorry. So if let's say this is the toughness A, that we consider that the ductile regime transits into the brittle regime, you can see that the ductile to brittle transition temperature increases. So this one represents the unirradiated sample. This one represents the irradiated sample. And how do we measure this? We use a Charpy test. I have a video in the description. Alright, so basically there's a pendulum-like looking thing that actually you swing against the material. Okay, so let's say you have a pendulum-like thingy with a notch. Alright, and then there's a piece of material here. So you let go of this this pendulum thingy from a fixed height, and then you see how high it goes. Okay, so this thing swings here, and depending on the height of this pendulum, you can kind of infer the energy that it took, to break the sample. Yeah, so that's the Charpy test for you. Okay, so yeah, so this is a BCC material, whereas for FCC, the unirradiated one will look like this. But again, there will be embrittlement as well. So BCC is for this, and this is for FCC. Okay, what we must note is that the ductile to brittle temperature increases, and of course the toughness will decrease even at high temperatures. So this is called the decrease in upper shelf energy. So that's the change or decrease in upper shelf energy, USE. So upper shelf energy decreases. Okay, so for typical ferritic steel, this is a alpha iron or BCC. Okay. Okay. When you look at the document by Oak Ridge National Lab, so they did some tests and they found that the delta USE is about 33%. It's a 33% decrease. The delta DBTT, that is about 82 minus 50. Okay, so this is the original ductile to brittle transition temperature. Okay, so at minus 50 degrees, the steel starts to become brittle. Now, after a neutron damage, it gets brittle after 82 degrees C. And now this is a problem, because when you pump water into the core during the ECCS event, the whole core, the reactor pressure vessel becomes brittle. So austenitic stainless steel is not shown in this diagram, except for this line on top. And yeah, you may wonder why does it happen for FCC as well, this ductile to brittle transition kind of test? Well, it all depends on the grains. So previously we have discussed that ductile to brittle transition doesn't occur for FCC materials. This is true, but this is true under the non-irradiation circumstance. But under neutron irradiation, the damage can allow intergranular fracture to occur. Okay, so what do I mean by that? Alright. So austenitic stainless steel, like most metals, they are made of grains. Okay? So I'm just drawing a few grains here. And within each grain, the FCC pattern will repeat. Okay? But between those grains, between the individual grains, we have grain boundaries. These are the lines I'm drawing over here. And these could be considered to be weak spots. And when the neutron hits this lattice, so when the neutron hits this lattice with the maybe 1 MeV plus of energy, what happens is that you will have Frankel pair generation, a vacancy and interstitial. And what happens is that you have all these 1D defects, for example the vacancies, they'll start migrating towards the grain boundaries, because that's where the what do you call that? Yeah, the defects like to coalesce at the grain boundaries. So in actual fact, what will happen? What will happen? The voids or the vacancies will migrate towards the grain boundaries. So between this grain and this grain, not only do you have a grain boundary, you have a void also. And well, within each crystal, you may have a ductile behavior, but on the whole, because the attractive force between each grain drops, we can have intergranular fracture. Meaning to say that the fracture doesn't occur within the grain, but rather between grains. Okay? Between grains. So that's what happens for a ductile to brittle transition, or rather, when the neutron strikes a FCC material, austenitic stainless steel, like the SS304 or something like that, Yeah. When that happens, the grains will get weakened. The grain boundaries will coalesce with the defects, and there'll be voids forming there, nucleating there, and this is where the fracture happens. So between grains, that's where the fracture behavior happens. So I've attached a paper for your reference in the description below. So for steels, just to recap, BCC is ferritic, while FCC is the austenitic. So you can think of FCC structure being the logical choice for nuclear reactors, because both FCC and BCC can exhibit this ductile to brittle transition. FCC, maybe it's more naturally resistant to it, maybe because the grains themselves do not exhibit the ductile to brittle transition. It's just that between the grains there will be voids formed, and as a whole material it becomes more and more brittle. That's one way of thinking about it. Alright, so during a reactor's lifetime, how do you measure this behavior? So if you have a reactor pressure vessel like this, okay, how are you going to measure this ductile to brittle transition? Are you going to, like, every year going to chip off a piece of the reactor and then you do your Charpy test? The chipping off may not be practical, because when you're doing that, you're actually damaging your reactor pressure vessel. Not viable. So this may not be a viable choice. So what do you do instead? Well, the normal practice is to have a few pieces of steel. Okay, a few pieces of steel. So this is steel that's made of the same material as this reactor pressure vessel, microstructure and everything. So they put a few lumps of steel into the reactor core where the neutron flux is the most. So every year or so, they will take one of these lumps of steel to go and do a Charpy test. That probably happens during a refueling or something. And you can imagine this piece of steel will be pretty radioactive. But that's the idea, so that you don't have to you don't have to damage your vessel. So now you can monitor the radiation damage of the reactor pressure vessel by taking a representative lump of steel inside the center of the core, where it's receiving even more radiation than this, so that it's a kind of a conservative estimate of how much radiation damage there is. Okay, so you can monitor the radiation damage of the RPV and kind of test in advance, or test how it reacts to thermal shock every now and then. So that's all I have for you. Thanks for watching this video. I'll see you next time. Bye bye.